Welcome to 6-7. This is a continuation of our work on linear equations, slopes of lines. And in this case, we're looking at fitting a line to data. You may have done this already. If in science, we may have had an opportunity to work through some data and try to fit a line to it. The first fit is to eyeball it. What you'll find is if you get a ruler where you can see through it, and see the graph underneath, and you have a carefully drawn graph, it can't be sloppy and you expect this to work, you will find that your ability to pick up the slope of the data is very, very good. If you talk to somebody else, you'll find you're in agreement about what the slope is. Then trying to get a line that splits the data kind of in half. So there's as much above the line as there is below the line. That's a little easier once you got the slope. In fitting a line, it doesn't have to actually go through any point. You shouldn't try to force it through a point because there really aren't any golden points where you know that those for some reason are absolutely right. You don't know that. So there's no golden point, so just fit it as best you can, draw the line. I think what you can find by this is we're very good at this. We people have a knack for seeing and fitting this kind of thing if you just give yourself a chance. So for activity 1, take a look at the data, graph it, and then draw a best fit line that you've done and compare your result to what's here in the activity. I'll wait right here. Don't worry about me. I got some coffee. I'm hanging out. You can just pause me and then come back when you're ready. Okay. Hey, welcome back. I hope yours fit. We look at this particular line that they've given us in the activity, and they show that it, in fact, doesn't pass through any specific point, but it does have a couple of easily discernible points, and one of them is at 1930, 61. The other's at 1990, 76. So, guess what we're going to do next? We want to get a line, an equation. So our next step is what we've been doing. We've got 2 points. Let's find out the slope. Put it into the slope formula. We find out the slope is 0.25, 1/4. Substitute that back in to the slope-intercept form of the equation so we can solve for b because we have 2 points. So we put in the value for one of the points. We do a calculation, we determine that b is a negative 421.5, and so now we have an equation for the line where y equals 0.25x minus 421.5. This gives us the ability now to estimate from this graph life expectancies for someone born in 2020. Well, this keeps going up. Do you really expect, what about 3,000. Is it going to keep increasing? Will it go forever? And if we go back in time, do we come to a point where people died before they were born? So the answer to those is no, we don't really expect this to be linear forever, but in small segments, this kind of data often is very linear, and you have to understand the weaknesses of extrapolating too far out. But it's a good way to, you got some data, see where it goes with that. So if you were born in 2020, your life expectancy is to be about 83.5 years, and we've got our results. It's simple, but it has a weakness in that a couple of different people will do different things. If you did it on your own, which you should have, compare it to somebody else's, see what they got out of their result, and you'll find you're a little bit different. Your slopes were probably pretty close. Your tilt or your up and down was probably off, which meant your y-intercept was off. Another way to do this, which takes away the guesswork, is doing a linear regression. And this is what's called the line of best fit in the linear regression model. And for this, you're going to need your TI-CAS, and you want to set about entering some data into it. And I'll pull up a CAS and show you what we're going to be doing with this particular result. And this is for activity 2. So you've opened up your CAS. Here's your initial page. We want a new document. We'll click on that. We want a list. We're not ready to do statistics because we don't have anything yet. So I'm going to put in the list. I'm going to leave it as A and B as the name. And this went from 1930 to 2000, so 1930. We put in our first value. We can put in our second value. And once we've got two in, we have a pattern. And if we can select both boxes, and this by hitting or selecting both of them, hitting Control, you can then get this little X and scroll down with it and release it, and you've auto-populated. Now I don't want 2010 or 2020. I just want to go to 2000. And the next thing we'll do is to scroll this back up, and now we have to enter our data in by hand. So let's see, 59.7, 62.9. This is where errors occur, is in the data entry. So be careful with it, especially with a short list. Make sure you go back and check it to see if you've perhaps made a mistake. So it's quite possible you could do everything else right, but have put in a couple of numbers in the wrong sequence. Okay, so let's see. I've got 77, 75.4, 73.7, 70.8, 69.7, 68.2, 62.9, and 59.7. So I got my data entered in to the table. I've got it right. Now I want to go and do the statistics on it. Okay, I've got data in. I'm going to go ahead and hit Menu. I'm going to select column A. I'm going to click on Menu, go to Statistics, to Stat Calculations, and I see that I got A. X list is A. My Y list will be B, and I need to go down here, scroll down, and my first results column will be C. I'm going to click OK, and I've got my linear regression, and the regression equation is the form of y equals mx plus b. M is about, well, it doesn't say approximately, it's 2.39524, and b is a negative 400.989. The r squared is the regression coefficient. It gives us the goodness of fit for the equation. But now we have enough to where we could write our equation from this, and this turns out it's not that far off from what we did previously, in which case where we got the b value of about a negative 429, so we're not too far off, but a little bit of difference. But in this equation, this linear regression equation is what's called a least squares regression fit. There's a little bit of discussion about that here in the book. We've rounded off our results, and so we've used linear regression. And we've got a table here that we can look at the two results. So we got our eyeball line of best fit, and they've given us some results for that, for the various life expectancies. And we can compare it to the actuals and see how far off we are from those results. We can carry it out into the future and see, but we can't get any kind of deviation from that. So we've got our eyeball, we have our line of best fit, and then we have our deviation. We look here at the guided example. It says, show that the sum of the squares of the eyeball line deviations for the life expectancies is greater than the sum of the squares of the best fit deviations. So the square of the deviation gives us a way to get a positive term for how far we are from a value. And back in the day, this was easier to do than absolute value. So we used squared values. This is kind of where it came from, and it neither here nor there. It gives us values that we can calculate fairly easily. And if we do the calculation for the sum of the squares line, you'll run through it for the values for the eyeball deviation. You're going to end up with, I don't know, what'd you get? You do the numbers? Got it? You there? Yet? Okay, I got 11.02, 11 and 2/100ths for the eyeball. And for the least squares, the regression calculation, I got 10.56. So when I do both of these, I'll get that. The reason this is called the least squares regression line is it's producing a line that will be fit to the data to produce the best possible least squares calculation, the lowest possible value. That's where the least squares line comes in. It means it has the least deviation from actual. That's our work today. That was the linear regression. If you need some help with a calculator, come see me, see another student. There's people that are pretty good with this. See if some people have some other ways to approach this using the calculator. There's a lot of paths to a solution in it. Best of luck. Good luck on the mastery quiz, and I'll see you in class.